Today, we're going to take a deep dive into solid-state battery technologies, and we're truly delighted to be joined by two of the world's experts on the topic. We are joined by today Professor Linda Nazar from the University of Waterloo and by Professor Jurgen Janek from the University of Gießen. Let me take a brief opportunity to introduce them. They are truly leaders in many aspects of battery technology. Linda comes from the background of solid-state chemistry, and for many decades, she has been studying the structure-property relationship of ionic transport. And over the past 25 years, she has investigated many different types of battery chemistry, ranging from lithium-sulfur batteries, lithium-air batteries, lithium-ion batteries in terms of cathode chemistry. She started all the way from lithium iron phosphate to all the high energy density technologies that is very actively pursued today. Linda is a member of the Royal Society. She has won countless awards and mentored dozens of students and postdocs who are now doing their independent research elsewhere in the world. And I have had the pleasure of knowing Linda since when I was a graduate student. And I'm truly amazed at all the contribution that she has made, and I'm delighted to hear from her today. Jurgen Janek comes from the background of physical chemistry, and is very well known for developing many techniques, both experimental and computational, to understand fundamental processes happening in redox materials. And in the recent 10 years, he has made significant contributions to the understanding of solid-state batteries, whether they are based on sulfides or oxides, and particularly understanding the importance of interfaces within those materials. Jurgen is the Dean of Biology and Chemistry at the University of Gießen. He also runs a joint industry lab with at the Karlsruhe Institute of Technology, the Bella Lab. So without further ado, I would like to ask Linda to start her presentation.
Good morning, everyone. Thank you, Will, for that very kind introduction. So I'll be talking about design rules for solid-state electrolytes, and I put rules in quotation marks because they're not so much rules as perhaps strategies. And I would especially like to start off thanking all of the people in my group that did all of the work that made this, that is making this possible today. So there's been a lot of, I'm not going to talk about solid-state batteries, that's Jurgen Janek's position, but I will just make a brief introduction to the topic. And this is an article taken from the Julian Spector about why Toyota's next move is solid-state batteries. Of course, there's less risk of fire because they don't have flammable electrolytes. They also allow for fast charge times. And in particular, the technology will allow one to stack cells, thus automatically improving energy density by a factor of as much as 2 to 3. And The Economist in 2017 asked if solid-state batteries will power us all. There's a nice article here. And they optimistically assumed that electric cars powered by these could be on the road by 2020. Well, we're not there yet, obviously, but that's what happens when you're a little too optimistic. So solid-state batteries rely on superionic conductors and optimized interfaces. And again, Jurgen is going to be talking about those interfaces. I'll be talking about the superionic conductors. So the concept is pretty simple. We have a positive electrode at some high positive potential, which is indicated here by red. We have a conductive additive, typically carbon, indicated in black. And at the negative electrode, we have the negative electrode material indicated in blue, again with some electronic additive. And the electrolyte runs completely through that cell. So the problem is, of course, developing good solid electrolytes, but it's also a problem of the interface, the triple phase boundary, where at the active material, for example, the positive electrode, lithium ions and electrons have to be simultaneously transported to that active material. And that requires very intimate interfaces. So while the reactivity of the electrolyte is not a concern, achieving this simultaneous transport is indeed a challenge. And if one has large secondary particle aggregates, that's also a challenge to obtain an adequate interface. So more specifically, there's also issues of chemical stability of the electrolyte with the positive electrolyte. There's oxidative stability issues of the electrolyte in the presence of carbon. And ultimately, one really wants to use lithium or sodium. If one is using a sodium solid-state battery, one wants to use a metal anode. And this presents its own problems because, of course, many electrolytes are not stable with lithium metal. Really, only garnets are shown to be stable, and and still dendrites will form. And so that usually requires the incorporation of some sort of protective interface. Those concepts are summarized in this slide with just a little bit more detail on the challenges. So the first point is that thick composite electrodes with a high active mass are really necessary in order to compete with today's lithium-ion batteries. So that implies that we have high ionic conductivity of the solid-state electrolyte in the order of 5 to 10 millisiemens. And we have this stable interface that I mentioned and low redox activity with the additive. The electrolyte itself, the membrane, needs to have good mechanical properties, and that means that ideally it is a relatively ductile material that will enable dynamic pressure control to be established, and again, these criteria for conductivity. So I won't get into these factors very much. I've already explained that lithium metal is using it as a negative is fairly crucial to really establish commercialization and a competitive edge for these batteries. And just a point that I think you're going to discuss in great detail is the fact that one needs uniform density over that interface. And I would just ask perhaps that glasses might be the answer, but I won't have time to talk about them today. And ultimately, good rate capacity and rate capability are necessary to compete. So we might ask ourselves, are these sorts of metrics achievable in a solid state battery comparable to that of a lithium ion? So again, the performance is limited by kinetics, not so much by transport across the interfaces, as I think Jurgen will be telling you. And of course, then we also have to consider the scalability of production of the solid electrolytes. So I won't be talking about polymer electrolytes today, not because they aren't a viable technology. They tend to have conductivities that are a little lower than what are desirable, but we work on the solid inorganic electrolytes. This is just a comparison between oxides and sulfides. And as you might imagine, one obtains better conductivity with a soft anion lattice, such as a sulfide, but better stability with a hard anion lattice. So examples of oxides include garnets, perovskites, nasicon type materials. These are all relatively chemically stable, electrochemically stable at a high voltage. They're compatible, as I said, garnets with metallic lithium, but they do have this unfortunate rigidity, the very high Young's modulus in the order of more than 150 gigapascals. And that makes them non-conformable and rather difficult to process into cells. Okay, so in the case of sulfides, variety of different materials have been examined. These are sensitive to moisture, unlike the oxides. They have high voltage stability limits. They will react with the lithium metal oxide interface, which means that sort of passivating layers are required, but they are relatively ductile with a low Young's modulus in the order of 18 to 25 gigapascals. And then a new player on the block are halides. And so the halides are also somewhat sensitive to moisture. They are encompassed by materials such as Li3MCl, where M tends to be a rare earth, and also halospinols, which I'll mention at the end of my talk. They actually are compatible with most cathode oxides, although they're not stable with metallic lithium, but they enable cathode oxide materials to be used without a protective coating. And they also have the advantage of good ductility. And the topic of today's talk, I'll be sort of going over many of these materials, but I guess one point just to remind you that all of these solid-state electrolytes have total ionic conductivities with negligible electronic conductivity, and effectively that gives a transport number of 1, which offers real advantages over most liquid electrolyte systems, which will not have a transport number of anything close to 1 and often in a vicinity of 0.4 to 0.5. So in order to achieve good solid-state electrolytes, that we need to have a facile conduction pathway for the mobile ions, which means a high number of carriers, a somewhat flattened energy landscape, which I'll be discussing. We need to have disorder in the mobile ion lattice and weak interactions with the framework, another topic of today's talk, and a polarizable anion sublattice, and I'll be talking about the role of anion dynamics. And in fact, I'll pretty much start my talk with that. So the first supraionic sulfide arguably is lithium germanium biophosphate. This was reported by Rio Giocano in 2011, and it really opened up the field. So this is often quaintly known as LGPS because of its formulation, and it's reported to have ion conductivity in the order of 12 millisiemens at room temperature. And so this makes that conductivity comparable to traditional liquid organic electrolytes. And the solid electrolytes are not affected by viscosity at low temperature, which gives them good low temperature performance, at least comparable to liquid electrolytes, if not better. So this is just a diagram from a recent paper by Rio Giocano and Toyota in Nature Energy in 2016. And this is what we call a Rigoni plot of power versus energy. And it compares all solid state batteries with a lot of other different technologies, lithium sulfur, magnesium, lithium air, conventional lithium ion batteries. And you can see that the solid state batteries perform really rather well under these, in this plot, especially at high temperature, but even under room temperature conditions, they show advantages in both terms of power and energy. So this is what's promoting all of the excitement in this area. So a few years ago, when we started looking at these materials, we started working on some sodium ion batteries, and we were aiming to find a sodium analog to LGPS. And we discovered this material, which is not isostructural to LGPS, but it actually serves as an excellent model, and I'll be using it as a framework to talk about anion dynamics. So its formulation is Na11SN2PS12. So you see the similarity in composition with the LGPS, but as I said, it's a new crystal family. And it has ordered PS4 and SN4 tetrahedra shown here in teal and in cobalt blue. And it has channels which contain different sodium ions. There's actually six sodium ion sites in this material. And these form channels that run along the C-axis and also along the A and the B axis. So it's a three-dimensionally conductive material. You can see that these channels are formed by face-sharing octahedra of the sodium that run in all of those three directions. And here's a better depiction of that along the A axis, where you can see that this is the window, the triangular window through which the sodium ions pass. There's also an additional site, which we call the sodium 6 site, which is a cubic site. It's not so important. So the point here is that the sodium 1 and sodium 2 positions are partly occupied. These are the ones depicted in sort of a light rose color, whereas the other three sodium sites in the lattice are about 95% occupied. So we have a occupied, partially occupied, occupied, partially occupied, alternating type of system or arrangement, motif in the lattice, which gives rise to good conductivity, in part because we lower the energy for defect formation because of these partial vacancies. The structure is reported by us in EES in 2018, and at about the same time, or just very shortly thereafter, by Stephanie Damon and Bernard Rolling's group. So we carried out AMID, ab initio molecular dynamic studies to understand sodium transport in this material. And you can see this is the sodium ion probability density. You can see that there's isotropic conduction as shown by this probability density in all three dimensions. And you can furthermore see that the experimental conductivity of 1.4 millisiemens is in very good agreement with that predicted by the AMID theory, which is 2.4 millisiemens. And similarly, the activation energy by theory of 0.2 electron volts is very similar to what we obtain, which is about 0.24 electron volts from experiment. So this is, as I said, a three-dimensional superionic conductor, and the diffusion coefficient that we obtain from AMID is about 2 × 10⁻⁸ centimeters squared per second at 300 Kelvin, in all three crystallographic directions. And that makes it somewhat similar, or very similar, I should say, to LGPS, but just in the LGPS in the basal plane. So one of the, as we started to look for other analogs to this system, one of the materials we discovered was the antimony analog, which is shown here. It was reported in Chemistry Materials about the same time. And we expected this to have better conductivity because of its larger cell volume, because of its larger cell volume. I have those numbers switched compared to the phosphorus. So this actually, this has the smaller cell volume, this has the larger cell volume, so you have to switch those numbers. So the point here is that the conductivity is about half that of the phosphorus analog, and the activation energy is much higher than that of the phosphorus analog. And this is also borne out by our theoretical calculations, where you can see that either the sulfide or the selenide have a lower activation energy of about 0.25 compared to that of the antimony analog. And the reason for this is actually shown in these maps. So these are maps obtained from neutron diffraction data. These are called, this is derived from the maximum entropy method, often abbreviated as MEM. And so this is effectively a map of the nuclear density. It's obtained from extracting the structure factors from the neutron diffraction data itself. And so what you see here for the phosphorus analog is the nuclear density for example, for the sulfur around the PS4 groups. So this is the red blobs here are the sodium ion density in the structure, and this green density at 300 K shows the rotational motion of the PS4 group about this phosphorus position. And you can see that at 3 Kelvin, there is even disorder obtained in that PS4 group, whereas at 300 K, that is rapidly rotationally disordered. And this is also true, of course, at 450 K. So we see this rotation at 300, whereas in the antimony analog, there is no motion whatsoever at 3 Kelvin, at 3 Kelvin, whereas at 300 K, there is only some disorder, but not actual rotation. So this provides, this is a real contrast between these materials, which we wanted to look into in greater detail, and that's shown on the next slide. And it relates to this concept, which was developed actually long ago and has been recently revisited, which is sometimes called the paddle wheel effect. And we actually prefer to make an analog more to a revolving door, in which the motion of the framework is actually aiding the mobility of the cations, just as one passes through a revolving door. So just to put things in context, the rotation of these anion tetrahedral moieties and polyanion materials in, for example, sulfates or phosphates was implicated in high temperature rotor phases. These individuals, Martin Jansen in particular, did a lot of work in this, Lundquist as well. So they were implicated in high temperature plastic phase of the sodium phosphate at 600 and in lithium sulfate, and quasi-electron neutron scattering confirmed this reorientational motion at 600 K in work reported by Jansen et al. And more recently, other using AMID and other complicated, sophisticated techniques, I should say, have looked at other polyanions such as the clozoboranes and also the borohydrides, Na3OBH4. So these are fairly recent reports. But it's hard to get direct proof for this coupling between the anion motion and the cation motion. And that's what I'll be talking about a little bit more today. So our so coupled with the MEMS, which I already showed you, this is the rotation of this PS4 group. So coupled with the MEMS, we carried out these AMID simulations at a variety of different temperatures, and we're actually able to see the onset of this paddle wheel effect. So this is just a snapshot, a 1 picosecond snapshot that shows that as this polyanion is rotating, the sodium is moving from one position to another in the lattice. And so these two processes are coupled. If one pauses or one artificially pauses the motion, the activation energy for that transport, the energy barrier, goes up, increases to 0.36 electron volts, whereas without constraints, it is significantly lower of about 0.2 electron volts. Now this is a little bit of an artificial imposition upon the calculation, but still it shows the point of of the importance of the polyanion rotation to lowering that activation barrier for transport. And the reason for why that activation barrier is lowered is observed when one actually looks at the structure. This again is in the picture that I showed you before of the transport along these one-dimensional chains. And the point is that as this polyanion, in this case the PS4, rotates, because it is edge bonded to these sodium octahedra in the lattice, it literally turns and opens up that window for transport in a transient way. So shown here is the antimony in blue and the phosphorus in pink. And you can see that that window opens up as the polyanion rotates for the phosphorus compound, but it does not open up for the antimony because there is no polyanion rotation. So the window remains effectively closed for the antimony where it opens up in the case of the phosphorus. And this is in large part what gives rise to the difference in the activation energy. And so one can summarize this by saying that the anion rotation flattens the energy landscape for the cation transport through the structure, and as I said, lowers that barrier. We have also looked at this effect in lithium-ion conductors. Specifically, we've compared beta Li3PS4, which is a superionic conductor, but only at 200 degrees, because the room temperature phase, which is the gamma form, is a very, very poor conductor. So it undergoes a phase transition at around 200 degrees or 250 in order to get to the beta form. We've been able to stabilize a version of this structure at room temperature, which has an equivalent roughly 1 millisiemens per centimeter conductivity. This is obtained by incorporating lithium into the structure and adding silicon to replace some of the phosphorus. So we're adding lithium and silicon into this lattice, and that has the effect of effectively splitting the lithium sites. And so the lithium sites in the beta Li3PS4 structure, each lithium site splits into 2 different sites, and that is equivalent to effectively increasing the atomic displacement parameter by a large factor. So all of the lithium sites are split by 1 angstrom, which is equivalent to effectively increasing the atomic displacement parameter. And this increases the lattice considerably, the lattice volume, and it stabilizes this effectively beta Li3PS4 type structure. So this is an entropically stabilized lattice with a geometrically frustrated landscape. And you can see in the gamma form, which is of Li3PS4, which is a very, very poor conductor, 10 to the minus 7 Siemens per centimeter room temperature. There is the MEMS map here show that there is absolutely no rotation whatsoever, whereas you can see that rotation in the high temperature, the so-called beta phase. At 200, this data was actually collected at 350, but you can definitely see the onset of that rotation. And if you compare that with the silicon substituted form, you can see the rotation is very evident in this silicon phase at room temperature, which also has about a 1 millisiemens conductivity at 30 degrees centigrade. So it is a similar effect to what I just described with the sodium. We again have a transient opening up of this triangular window, which is where the lithium ions pass in this structure. And so when we pause the rotation, the window disappears or diminishes. When we let the polyanion rotate, this is through AMID calculations, the window opens up. And this is what lowers the activation energy barrier. And we notice in the power spectrum that we see the same frequency range for that rotation, for the rotation of the polyanion groups as we see for the lithium in the material. So that again is evidence for the coupled mobility. And the 2-dimensional probability distribution of this phosphorus to sulfur to lithium angle and the distance between the sulfur and lithium atoms in the first shell also shows the same sort of effect. Effectively, that shows that the groups are highly delocalized, which signifies a strong correlation between the polyanion and the cation. If there was no correlation between polyanion mobility or rotation and the lithium, we would simply see this localized in a discrete spot. So the fact that this is delocalized is evidence of this, this correlation. So time is moving on. I will switch to flattening the energy landscape. This is just a picture of a golf course, pointing out that we don't want to get into these little energy traps or these sand traps. And I'll talk about the agurodite lattice. In this material, it is this material. This is a diagram from Wolfgang Zier's paper. You can see the polyanion tetrahedra, the PS4 groups in this structure with these Frank-Caspar tetrahedra in which the lithium ions reside in all four corners of the cubic structure. And these Frank-Caspar polyhedra have usually two different lithium sites called a 24G and 48H site. This is the 24G site here, the 48H sites are here. And this material is quite popular because it forms a passivating quasi-stable interface with lithium metal, because these insulating materials swarm and do not continually grow. This is shown by Jurgen Janek in a nice paper. And he's going to be talking about that a bit more. And there's also been anion dynamics, which have investigated polyanion rotation. So there is an intercage jump in this material, which is thought to dominate long-range transport. So disorder on either of these two sites will determine the ion conductivity. And if we have iodine in the lattice, though the iodine is localized on the 4A site, whereas sulfur is on the 4C site, whereas in the case of chlorine and bromine, there's delocalization over those two sites, and that gives rise to very high conductivity. So my grad student Lidong Zhou discovered that we could make highly conductive iodides using the antimonide version of this material, and these have conductivity upwards of 10 millisiemens per centimeter. This shows the diffraction patterns of the antimony, the germanium, and the tin analog, the silicon, germanium, and tin analogs, and the superionic conductivity is shown here as high as almost 15 millisiemens for this particular composition. And so the point is that when we substitute antimony with the smallest aleovalent dopant, which is silicon, that gives rise to the highest lithium content, as you can see here, and that gives rise to the highest conductivity. And grain boundary effects are important. This just shows some impedance data where we can separate the bulk from the grain boundary. So in fact, there is considerable grain boundary effects. In other words, there's low conductivity, especially when we get to higher values of silicon. But at these conditions, we can, by sintering the pellets, we can get conductivity upwards of 24 millisiemens per centimeter. So improving the grain boundary contact certainly increases the ionic conductivity, but the bulk is excellent. And this is achieved with a very low degree of anion disorder between the sulfide and the iodine. So comparing the structures of the pristine agurodite with our silicon and lithium substituted material, we see that we have 4 sites in the case of this new silicon substituted material, where only 2 sites in the pristine material, and these are indicated by these arrows. And again, this is achieved with very little anion disorder. So the reason for this increase in conductivity is that we have these additional sites which lie between these Frank-Caspar polyhedra. These are the cages that are shown here. And so whereas we would normally have these jumps within the Frank-Caspar polyhedra and also some intercage jumps, the addition of these new sites through a phase-sharing tetrahedra, it's a little hard to see, enable this initial pathway. And so this allows a concerted ion migration path to take place because we populated effectively these high energy interstitial sites. And this activates a concerted ion migration, which was reported by Yifei Mo, also by Gerhard Cedar, and lowers this activation energy for lithium ion diffusion. So we've also looked just briefly at symmetric cells of this electrolyte together with lithium. And we were able to achieve current densities upwards of 0.6 milliamps per square centimeter over as much as 1,000 cycles. So this again indicates we have a quasi-stable interface formed between this agurodite iodide and the lithium, likely due to the formation of lithium iodide and perhaps some lithium antimony phases. And Jurgen Janek will be talking more about those interfaces in the next talk. So I'll just end off on some halide materials. Also an agurodite, starting from this chloroagurodite. the different strategy here is to increase the halide concentration in this lattice, which actually increases vacancy. So whereas in the case of the antimonides, we have a lithium-rich agurodite, in this case, we have a lithium-poor agurodite. Again, as I said, it creates vacancies on the lithium sites, about 10%, and it makes the material chlorine-rich. And you can see that the chlorine distributes on both sites, the 4A and the 4C. So we're not really increasing the anion disorder, we're simply putting more halide into the lattice. And so the activation energy drops as we add the halide, and the conductivity dramatically increases. So we are at about conductivity of about 9.4 for the highest chlorine concentration that we can achieve, which is the chlorine 1.5 phase, and that goes up to about 12 millisiemens for sintered pellets. And so this value of 12 is between the highest conductivity of the LGPS phases, either this material or this material, which are reported in that Nature Energy 2016 paper that I referred to earlier. And the reason for this are obtained from PFG NMR measurements, where we actually quadruple the diffusivity. These are experiments done in collaboration with Gillian Goward's group at the McMaster University and her grad student David Bazak. And so this is just a plot of the diffusivity obtained from these PFG measurements, and you can see that it's definitely the highest for the chlorine-rich phase. And the value of diffusivity of 11 times 10 to the minus 12 is actually higher than that in LGPS or in this lithium silicon LGPS type, or this other type of structure. So the diffusivity is about more than threefold, and that basically correlates exactly with the increase in the conductivity that you see plotted here in this bar graph. So the take-home message is that the anion disorder and weakened interactions between the mobile ions and the framework lead to a quadrupling in the ionic conductivity. And when we examine this material, by using CV, we could see that there was much less current passed for the chlorine-rich versus the pristine agurodite material, especially after this is the first cycle and this is the second cycle. So you can see that we're forming a passivating layer, and we have better anodic stability with, due to this higher halide content. And so that inspired us to look at pure halide materials. And so I remind you of this plot of energy here, or a redox potential, that we're really trying to stabilize materials at these higher potentials. Halides are not typically stable with lithium metal. But you can see that in the CV that we now have an onset of oxidation that is about 4.3, at least volts, versus the roughly 2.5 to 2.7, which is seen for a typical phosphate. So this enables us to obtain coating-free cathode solid-state batteries, and with development of a new lithium metal halide structure. So I will skip over this slide just in the interest of time. The point is that we're trying to develop not only solid electrolytes, but also coating materials which can have advantages over things such as lithium niobate, which are difficult to control the quality of as one puts coatings on cathode materials. So lithium metal chlorides are a relatively new player in the field. They were actually investigated in 1997, 1992. And Andy Sun came up with some nice work on the lithium indium chlorides at about the same time that we published work. And all right, there is a Panasonic paper here cited in Advanced Materials. But in this work, we've substituted zirconium into either the yttrium or erbium structure to obtain conductivities upwards of a millisiemen per centimeter. So these materials, this just shows that they're basically isostructural in the case of yttrium and erbium. This shows X equals 0, in other words, the pure yttrium. This shows the zirconium substitution. And you can see that there's a change in phase as we add the zirconium to this lattice, and that is concurrent with an increase in the conductivity up to about 1.4 millisiemens at the highest levels of X of about 0.4 to 0.5, in other words, zirconium concentration. And these are accompanied by a very low electronic conductivity of in the order of 10 to the minus 10. And this data is effectively replicated for the erbium material. So this is a new structure, and this just shows the lithium ion conduction pathway. So we create a tetrahedral lithium ion site in this lattice shown by lithium-3, as opposed to the pristine material, which just has lithium-1 and lithium-2. And so the pathway here is shown in these red arrows. It's effectively a one-dimensional conductor, but there is limited conduction in the other planes. And so this is a bond valence energy landscape map, or energy plot, and you can see this lowered energy barrier for conduction compared to that between lithium-1 and lithium-2, which is upwards of 0.6. So this lower energy pathway is what enables its conductivity of about more than 1 millisiemens to be obtained. And we then looked at this material with lithium cobalt oxide as a positive electrode. This shows the data for the erbium and for the yttrium. And you can see that, especially in the case of the yttrium, we're able to obtain rather good performance, electrochemical performance, with as little as 15% of the electrolyte. And especially you can see that in the impedance data, the EIS, we have reduced charge transfer for the halide compared to a solid electrolyte where we're using just lithium phosphate, and that's less than 1/20. So that's we've really decreased that interfacial impedance dramatically in the cell. I might add that what we're comparing here is the cobalt oxide with either the halide in the cathode or the lithium cobalt oxide with the lithium Li3PS4 in the cathode. In both cases, we're just using Li3PS4 as the membrane in the cell. So at rates of 0.5 C and 4.3 volt window, we're able to obtain stable cycling capacity. And we've since translated this to a new lithium disordered halo spinel, which is, I think, the first in its class. The structure is shown here on the left. Again, conductivities of on the order of 1.5 millisiemens, activation energy similar, about 0.3. And this shows the data for NMC 622 and for a high nickel NMC material, NMC 85 concentration of nickel. And in this case, we can actually cycle all the way up to 4.6 volts with reasonable stability over 70 cycles. In the case of the high nickel material, we're able to obtain capacities upwards of about 200 milliamp hours per gram, again over roughly 70 cycles. And this is in the window up to 4.5 volts. So even though these electrolytes have a thermodynamic stability window that seems to be about 4.3, clearly there's some kinetic stabilization that enables to take us up to 4.5 or 4.6 volts. So with that, and 2 minutes left to go in my 35 minutes, I'll just briefly summarize by saying that we have some new descriptors established. I would remind the audience of the need for high ionic conductivity to obtain high current densities. The issue with lithium metal does need to be addressed. And I've highlighted all of these points: increasing the vacancy population, strategies to increase conductivity and stabilize interfaces, for example, with halide materials, controlling cation disorder and anion disorder, the importance of anion dynamics, and polyanion rotation, which can enhance the conductivity by a factor of 2. And one solid electrolyte is unlikely going to overcome all of these challenges, and so bifunctional or dual electrolytes are probably necessary. So with that, I'd like to again thank all of the people that did the work. I'm just doing the talk, and I'd also like to thank people at ONRL who helped us get neutron diffraction data, our colleagues at BASF, my entire lab group shown here, and BASF and J. Caesar in particular for their funding. And thank you for your attention.
Linda, thank you so much for that deep dive into ionic conduction and solid electrolytes. And we have received more questions than we can possibly answer in the short amount of time. So as the moderator, I have the difficult task of picking out the question for you. So forgive me if I pick out too difficult questions. So let me start with a very high level question. One of our viewers is asking, what has been the success in predicting new solid electrolyte via simulations? You show some really beautiful work of ab initio MD for understanding transport, but could you comment on how that has led to discoveries of electrolyte?
Well, that is a very difficult question, Will. And I would say that there's a lot of hope for the predictive capability of simulations. But at this point, they have generally proven more as a guideline to interesting materials that may be superionic conductors that turn out maybe not to be they don't have as quite the conductivity that the simulations predict, but it does give us, you know, kind of a guideline in an approach, a strategy, or target materials to target, even though sometimes, as I said, the conductivity is not quite what was anticipated.
Thank you, Linda. And the next set of questions concern the first part of your talk on the rotation and hopping coupling. So the first question is, can you expand upon the role of rotation on phase stability relative to ionic conductivity? I think you showed a quick 2 figures on this.
So the question is on the role of rotation to phase stability. That's a harder, well, if we, that's a very difficult question because we don't really, I would say that answer is not clear. In the case of the, LGPS does not seem to undergo any polyanion rotation, and yet it's a relatively stable material. In the case of the lithium and silicon substituted beta Li3PS4, we stabilize that rotor phase down to room temperature, but that's really an entropic stabilization in large part because of the fact that we have the silicon and phosphorus in the lattice. But because we are sampling different rotational states of the polyanion, we can see that in the phonon modes, there is probably a contribution of that rotation to the overall stability. So I would say that there is probably a contribution, but it is not completely quantified, or it is not well quantified.
Thank you, Linda. And on a related question, in terms of the rotation dynamics, can you comment on its contribution to the temperature dependence? And specifically, how does that contribute to the activation energy in terms of both the rotation and the hopping?
So you're asking if the rotational dynamics contribute to the temperature dependence. Effectively, as things rotate faster, does that help? Does that aid the conduction? We have not yet quantified, and we would be doing this with AMID, so we have not quantified the rotational speed, so to speak, with the effect of the cation diffusion. So experimentally, of course, conductivity is going to go up as a function of temperature. But I think what that question is really addressing is whether or not we have quantified this by AMID, and the answer is we have not.
Okay, I'm being told we are almost running out of time, but I will squeeze in one last question. Your talks discuss a lot of the dynamics in terms of the hopping contribution and to the conductivity, but can you also talk about the effect of carrier concentration? So in terms of the amount of disorder, and what type of dependence do you see of the ionic conductivity on the amount of disorder in the standard ionic conduction picture?
Well, of course, carrier concentration is extremely important. If only a portion of the lattice is involved in that conductivity, then in the conduction mechanism, you don't end up with a very good conductor. So the whole approach of disordering lions in the lattice over many different sites, for example, in the antimony agarudite, is to do just that, to increase the carrier concentration so we invoke a larger number of participatory ions in the process. And in the case of the halides, we actually see a situation where, again, by increasing that, by generating new sites for lithium population and invoking those ions in the pathway, we increase the carrier concentration, even though in that case, some of the lithium ions are immobile and they just form an immobile framework. So the short story is really important.
Thank you, Linda. And for our viewers, the many who we could not address the questions, we apologize, but I'm sure Linda will be happy to answer your questions by email if you reach out to her. So Linda, thank you once more for the deep dive into the solid state chemistry of ionic conductor, a crucial part of enabling solid state batteries. Here at Stanford, we're very concerned about all aspects of technology translation, being in Silicon Valley. So I would like to ask the first question on translation and the second question on policy. I know this is a bit different than the technology focus of today's talk in the material science and chemistry. So my first question to the both of you is about the cost learning curve. So we know that the cost of solid state battery is not known today. It is difficult to estimate. But I can ask you to assume sometime into the future, commercial activities are becoming more mature, commercial products are delivered. How do you think solid state battery can compete with the cost learning that is in the incumbent technology in lithium-ion batteries? So as the costs begin to fall for solid state battery, so does lithium-ion battery. And that is a very severe and rapid cost learning curve. And there is a cost floor for lithium-ion battery, but there's still considerable room. So I was wondering if the both of you can talk about, for technology like solid state or maybe other energy technology, how do we compete with another technology that is incumbent, that's a $50 billion industry, that is also learning at the same time?
Well, I think this is the same as probably in all other technology fields. I think new solutions always have, difficulties in competing with the existing ones, of course. So we see currently the fight of the electric vehicle with the Otto motor, which is more than 100 years in operation and is being further improved. So I think, in fact, once the solid state battery will not have substantial advantages, it will be difficult, I think, really to have in sufficient time the sufficiently steep learning curve to be also economically competitive. I think in the current, at least materials cost of batteries, the cathode is the most expensive part, and the electrolyte is only, so to say, taking a small share of the cost. If a solid electrolyte would change that picture too much, then this is already a significant disadvantage. So the solid electrolyte should not be really more expensive, which, I think this is an important point. So, and I think in the FESPAT cluster in Germany, the cost issue is in fact something we also deal with. We try to understand, in fact, the cost issue. Well, I'm not a specialist in techno-economics, so probably I'm not the best to answer these things. I try to find good solutions and try to understand which route one can go. But as I said, it's not, I would say, it's not a simple automatic route for the solid state battery. But we are really in an early state. And of course, industry is always impatient, I would say, but we still need some time. But we should, of course, in order, I think, to understand economic potential success, we should not forget the cost of it, cost issues, yes. And I'm happy if people make solid, I would say, techno-economic models that are reasonable. But upscaling changes things. So, for example, I remember that the solid power guys, and I really like their work in the US. Last year on the conference, they were worried about the price of lithium sulfide, because that is was an important part of the cost of preparing thiophosphates. And the recent conference, that was not anymore changed, was not anymore mentioned. So that simply means there must have been now, or there must be a cheap source of lithium sulfide, which before that was just a fine chemical. So with upscaling, often things change, and that has to be taken into account. And this is my comment. Maybe Linda has another view on that.
I think you've described it pretty well, Jurgen. I think my view would be that the rate of drop in the cost for traditional lithium-ion batteries is slowing to some degree, whereas it's when that rate of change, the drop, it's, in other words, the rate of the drop is going to be much higher for solid state batteries. And at some point, one assumes or one hopes that they may cross over, because there's so much more to be learned in solid state batteries. And indeed, upscaling of the solid electrolytes is very important. And I think we're not at the stage yet of even having defined the ideal solid state electrolyte. So I see that coming down, that the drop in costs, especially with processing costs, coming down very rapidly, whereas I think we're coming down in lithium ion, but at a much more gentle level now, sort of scaling out. So I think that would be my only additional comment to what Jurgen has said.
Linda and Jurgen, thank you for painting this cautiously optimistic picture, of course, highlighting the role of chemistry behind all that. In the few remaining minutes, I thought I would turn your attention to the policy side of things. Mm-hmm. And I'm sure there is not a single participant here and our viewers that are free from the pandemic. And we have seen some very encouraging and exciting reports where the response to the pandemic is also being coupled to the response to issues of energy and sustainability. The European Union, for example, has announced major initiatives in this area, as many other countries. I was wondering if the both of you can talk about looking forward, what would be your recommendation to the policymakers, how the two can be coupled in a way to accelerate the recovery and also our advances for clean energy?
So maybe now Linda may start.
That's because it's a more difficult question, Jurgen. Well, you know, as Mark Kearney has said, you know, eventually COVID will be controlled, but climate change remains the real pandemic that's on the horizon, and so to speak. So in terms of establishing sustainability for the future, there is obviously no question amongst policymakers, I think, and scientists alike, that electrochemical energy storage is part of that solution. And that is ever going to be more important, whether we're in a day and age of COVID or not. I mean, I would say, in fact, perhaps even increasingly more so. We're going to have to think about, obviously things are going to change, at least in the short term and perhaps in the long term. But in any case, energy policy and sustainable energy policy has to be part of the solution. That goes without question. So I don't know if Jurgen has things to add.
Yeah, maybe what comes to my mind is simply that, yeah.
Sorry, did I answer your question, Will, or were you after something else?
No, this is great. Linda, thank you for sharing. Jurgen?
Yeah, I think what comes to my mind is, first of all, that I think that it may look that the COVID, let's say, period helps. But I think on the other hand, I think at least in Europe, we have this very strong trend towards public transportation and even discussion for free public transportation to, I would say, reduce individual transportation that, of course, is worth with respect to carbon dioxide or the carbon footprint. And I think the COVID period, of course, is a strike back because people have the tendency for more individual transportation. So I think in Europe, we see, maybe even in the US, we see more bikers, e-bikers. And so I think that's not very supportive. So I think the trend of more public transportation, electric buses, I think is a big wave coming with interestingly solid state batteries entering into that with polymer electrolytes. I think it's not so simple with the COVID. It looks as if that helps to advance alternative things, but partly it also leads to strike backs, I think.
Jurgen, do you get a sense within the EU that there is an injection of funds and resources as a way to restart the economy specifically for technology like batteries and future technology like solid state batteries?
Yeah, absolutely. This is the case. I think these big programs that are currently being advanced, I think Europe as such, they had the idea really only in principle to put, I would say, really substantial funds into the support, I would say, of, well, environmentally benign technologies and things. And I think in Germany also, I think there's electric cars are being supported, and there is the idea to support, I think, environmentally friendly. There's of course always a struggle because of social issues have to be considered. But by and large, I would say that there is a strong sense for that in Europe. Yes.
Well, I
and
think
that goes that will definitely also, I would say, be translated into funding. Yes, I'm sure.
So it sounds like there's a combination of push and pulls as a result of the pandemic.
Yes, right.
But I think we're all hopeful that the two can be somehow coupled between the recovery and also progress for clean technology. So we are out of time. Linda and Jurgen, I'd like to thank you once more for joining us from Canada and Germany and to entertain our viewers with exciting results, a 6-course meal, and it's been really a wonderful journey for the past hour and a half. So thank you both very much. So just a quick announcement, we will have our next symposium also on Friday, June 12th, the same time, 7 a.m. Pacific. And we will be joined by Professor Claire Gray from the University of Cambridge, and also Professor Gerrit Sater from the University of California, Berkeley. And they will continue on our excellent theme so far of understanding materials and chemistry for energy storage technology. And on that note, I'd like to thank everyone again for participating, and we hope to see you on June 12th. Thank you very much.